let's see. So I have finished soldering up my SD card reader shield. So this is what it would look like. You may have also gone ahead and you may have also soldered up just the proto shield, the one that just has holes in it. It would sit on top of this one if you wanted to do that. It's not terribly difficult to do, but you do want to make sure that you don't have cold solder joints. So basically on the bottom here where you solder, if there are blobs, those are probably not good. You want little cones that are melted. Basically you want the little ring in the board to be connected to the pin that's sticking through the header with solder. And it's totally possible you do everything correctly and it still doesn't work. That's just, this is actually the second one I built. The first one I built, just for no reason that was detectable, it didn't work. So some of the things I've seen with these being a problem is this little resistor right here being missing. So up there, just not being there, just the open solder pads. These two are missing on all of them. I'm pretty sure that no one has anything there, and that's okay. But this one missing means that it's not going to work. If for some reason yours is missing that, you've already soldered it up and you don't want to change it out, just bridge across it, just solder across the two pads so it would look kind of like these over here, and just solder across it. So that's this little resistor right here. If it's not working, you don't have any cold solder joints, so you think you've gotten all the solder done correctly on the headers, then the other stuff that goes wrong is there's been a couple we've seen that these little pins, across down here where the card itself, the card reader itself mounts, sometimes those are disconnected. Probably are not going to be able to reconnect those. What you need to do to test it, well, first of all, just plug the shield into the Arduino and run the basic blink program or something, just something works. So remember, let's go back to Arduino. So here's the Arduino IDE. Oh, is it going to be super tiny? Let's see. So if you remember, you do have to go into tools and make sure you've got the right board and port. So mine actually isn't plugged in, so we need to plug it in for it to do anything. Oh, and I mounted mine on this little piece of masonite board just because if you set the Arduino down in here, these tables have they have a stainless top on them, and you don't want to sit them directly on the metal. So I mounted mine just with some standoffs. These are the same standoffs that you could probably have on the robot from 120. I don't know if you have 4 of them or not. Mine actually has only 3 on there, but you could get away with 2 or something. You just don't want it to. Some of these Arduinos come with cases. You just don't want it sitting on the metal because all the pins on the bottom, I don't know if you can see it, but on the bottom down there, they are all exposed. And if you sit them down on something conductive, then they will all connect and it's not going to work. So mine's mounted this way, and I put the breadboard on there. You don't have to have these little particular pieces of masonite, but you might want to think about some way to mount it. So the first sign that something's going right is that you plug it in and this little LED comes on. So that's a good sign. That means it at least has power. But then you want to do, you don't even have to worry about writing anything to the card. The next thing you want to do is something like the blink program. So over here I've got, I was talking about file. We're on I assume everyone's running an Arduino Uno. So I'm on Uno, and then whatever port it comes in on, COM port 5 for me. Yours are going to be different. And then just get the example code, basics, and just the blink one. The blink one's good because it doesn't need anything other than the board. You don't have to connect other stuff to it and to tell it's working. So get blink. It's already loaded here. And basically, it's just a code here that goes in, turns one of these pins, the built-in LED pin, to an output and then blinks it on and off in 1 second intervals. So then you want to upload that, so it'll verify, compile it, and then hopefully upload it. Hopefully. It's kind of, there it goes. All right, so it's uploading, done uploading. So what you want to happen is that, and then you want to be able to go down here and, let's see the little LED? No, I don't see it. Where'd it go? It's in there. The USB cable's covering it up. Oh, there it is. So it will blink at whatever interval you put into the code. It was in Arduino itself, so I'll show you. So in the IDE for Arduino, File, Examples, Basics, Blink. Well, I split off of it. Basics Blink right there. So it's already pre-written in the Arduino IDE. I'm not sure what version of the IDE I'm running, but it's new enough. There's probably a newer one than what I have on here. Light. I guess it's not going to be much clearer than that. So what that'll tell you is at least there's nothing in your soldering job that is shorted out or something like that. So you're able to load code to the Arduino. It's not actually using the SD shield, but the first one I put on here, I built it just like this one, put it on there, and the Arduino wouldn't accept code at all with the shield on there. So there was something internally wrong with the SD card that was shorting some of the pins on the Arduino, and it wouldn't let it receive code. So if you can get that far, you're still good. The next thing to try is this. So on Moodle, we've got, let's see over here, we've got SD write. So I've got it on today's class, number 14, SD write. So this is some Arduino code. Let's copy it and make us a new sketch. Oh, came up over here. Let's make it over here. See if I can make the font bigger. I don't remember where exactly that is. Preferences, font. Let's make it 28. Okay. All right, there we go. So what this little code does, and it's all pre-written, it has 2 include files, one for SPI, that's serial peripheral interface, we'll talk about that in a second, and then one for specifically for SD. I think you already have those like built into the Arduino IDE. You don't have to go download them somewhere. I don't remember downloading them, so I think they're already in there. Here's just labeling a pin, number 10. That's one of the pins that the SD card uses. In your setup, we are going to do serial communication. So we're going to communicate at 9600 baud. And then this is just basically waiting for the serial communication to be established. And then while it's not established, then wait, basically. So it waits for it to establish. And then once you have serial communication running, then it will print on, assuming you have the serial monitor, so tool serial monitor, assuming you have that thing running, which is off the screen right now. So it's blank right now because there's nothing happening on COM5. But assuming you have the serial monitor running, then it'll print, oh, well, it won't print that. It'll print initializing SD card. So it'll give you a little readout here that is trying to figure out if there's an SD card to write to. That's what this little bit of code does. If the SD, so this is part of the library that we imported, if it doesn't begin on CS1, which we said CS1 is pin 10. So if it doesn't begin, then there's something wrong. So it'll display this message. So if you had your SD card shield and it was working fine, but you didn't have the SD card actually inserted into the reader, then it would give you this message. Or if there's some other problem with communicating with the SD card, then it'll give you this message. And basically, then it goes into this infinite loop of it's not working. Assuming that doesn't happen, then it'll print that the card's initialized. And then it's going to go to create a data file, open, here's a name. This is how you're going to create new files on the SD card, and you're going to write to it. It's going to write all your base are belong to us from, oh, I can't remember what game that's from. It's a bad translation of a, yes, and I can't remember what the, we'll have to look it up later. But it was a bad translation of a video game back before y'all were born, probably. Anyway, let's see. So if it's able to create the file, then it'll write to it, and then it will, if it is not able to create the file, it'll say error opening the file, or if it's unable to open it, then it'll give you this error. And then there's nothing in the void loop down here, so it doesn't repeatedly do these things. All of this is actually in the setup. So let's try this one. Oh, let's get our serial monitor so we can watch. It's gonna make it so that we can see all of this stuff. Got so many things open. All right, so that one. Oh, I need to save it. I'm going to put it in the same folder I've got everything else in. That's fine. I don't care. Sketch September 24th. That's fine. So it's compiling okay. Then it's trying to upload. And if you see your TX and RX lights, you can't, well, I don't even have the screen on it, but actually, let's just go to the, all right, so it initialized it, it was initialized, and then it printed our little text message. So now I should be able to eject the SD card and read it, and there's that myfile.txt or whatever the name was on there. So this little bit of code, this SD write, will be the base for you writing data from the wherever sensor. We're going to use the thermistors first, so whatever thermistor sensor data you have, storing it on the SD card, and then you can read it off of the SD card later. There's actually a separate program on Moodle. Let's see here, SD read, that takes a file and reads it in. Or, I mean, it's a text file. The way we saved it there was a text file. You could just take the SD card itself, read directly from it on your PC. So you could put the SD card into a SD reader on your PC somewhere and just read the file that way. Or there's a Arduino sketch that will also do that. What else is out here? Let's see. Some stuff about the SPI interface. There's homework problem 2. There's another serial write. Let me see what that is. Oh, this is actually, so what you have to be able to detect is this Arduino or Python. So when you see the void setup, void loop, those are going to be the Arduino sketches. Python doesn't really use that construct for how they're going to loop around things. So this would be an Arduino code. What this is doing is it's basically, this goes along with the document from a previous class, not this one. Oh, there we go. It goes with, is it class 4? Let's see. Nope, maybe it's class 5. No? 3? Oh yeah, so this numbering systems, number conversions, character encodings, those are the ones I'm not going to read to you. Basically, those are talking about the different binary, hex, decimal, and how to translate between the multitude of whatever base system that you want to translate between. And then that one that we just looked at right here is using Arduino to write in various, like there's the decimal system, there's the hexadecimal and binary. And so these numbers represent characters in the ASCII system. So that's what the character encoding document is talking about over there, character encoding. So you do need to read these. They're like 1 page each. And if there's stuff if you don't know how to convert binary to decimal and vice versa, or hex to either of those, or some generic like a base 7, you just make up a system, then you need to look through those and see how you convert those without, going to Google or whatever. How do you actually do it by hand? So that's what those are. Let's see, what else is in here? So that's that serial write thing. I'm going to close some of these tabs, getting too many things open. Let's look at the SPI interface. I actually put a link down here to a SparkFun version of this thing. SparkFun is just a website where you can buy things like this SD card reader. I don't think we got these from SparkFun, but they have similar stuff. But they have a good piece of information on SPI. We're going to look at this one right here, I think. Right, here we go. And again, I'm not going to read all of this. We're just going to look at some of the pictures. But basically, SPI is Serial Peripheral Interface. And it's so the big thing about it is this word right here, synchronous. So most serial communication that we've done is asynchronous, meaning that it's not timed together, it's not synchronized. So we did, like when we just wrote that code, or we didn't write it, we looked at that code, it had the 9600 number in there. That was synchronizing up talking and listening, basically, so that you're talking and listening at the same rates. If one of your elements, maybe your microcontroller, is listening at one speed and your sensor is talking at a different speed, then you're either going to get extra data, you're going to miss the data, you're going to get incorrect data somehow. And so there have to be these protocols. Normally what happens for asynchronous stuff is that the part of the data you send is the message, hey, I'm about to send you data. And then another part of it is, hey, I'm done sending you data. So it's part of the data itself is this message of, I'm sending you something, listen to me, and then now I'm done. So it gets a little bit extra overhead in there because you have to send more information to talk. It's good in that you don't have to be synced up. You can send information kind of on demand whenever you want to. But you do have to, once you send it, there has to be something that tells the receiver that, hey, I'm sending you stuff and I'm done now. The SPI is synchronous, so the sensor or whatever it happens to be and the microcontroller are synced together. So that's good in that you don't have to worry about sending start and stop bits or whatever you're sending. You don't have to worry about this synchronization. It's already happening. Basically, usually the microcontroller sends out the synchronization signal, and it can talk to multiple sensors, or I'm using sensors. They don't have to be sensors, but in this class, they're basically going to always be sensors. So you can talk to multiple sensors over one clock, basically one clock signal. And well, I guess the SD cards, those aren't kind of sensors. Those are more storage. So you see basically this type of setup where over here you've got what is for us going to be the Arduino, and in the green you've got what is going to be the sensors or the SD card or whatever. And so the S clock is the serial clock. So you see the Arduino initiating a clock signal. And so this is like a periodic pulse that can be sent out to all the SPI devices so that they're all synced up. And then you've got the MOSI and MISO. I don't know if you actually say them that way or if you say MOSI. I don't know. But I'm going to say MOSI and MISO. And so what you've got there is the master out. For us, the master is going to be the Arduino because it's the one controlling the synchronization of everything. And it's sending out information over that line. And then the master in is all the sensors or the SD cards or whatever sending information back to the Arduino. So sensor data comes back to the Arduino, or SD card reads come back to the Arduino and then go wherever they need to go. And then this last line down here is the select line. So it's basically which one of your, this diagram only shows us being connected to one SPI device, but it could be connected to, many SPI devices. And so this line says, which one do I want to talk to right now? Do I want to talk to the SD card? Do I want to talk to the thermistor? Do I want to talk to the accelerometer? Whatever it is. And so this is kind of the generic setup for SPI. So the difference that you see right away is it takes 4 lines. So you not only do you need well, and that's outside of any kind of power requirements that it might need, but 4 data lines. So 1 for the clock, 1 for the Arduino to talk to the sensor, 1 for the sensor to talk to the Arduino. Now this part's good though, since they're separate lines, you can actually do them at the same time. So you can actually send commands to the Arduino to go collect data or whatever. At the same time, the sensor is sending data back. So you can actually get some advantages using that. And then a 4th line to tell the sensor to actually be active or not. And this is a line that's normally, I believe it's active low. So normally this line is high, meaning like 5 volts in our system. And that actually turns off the sensor. And then whenever it pulls it low, this select line, whenever it goes low, then the sensor is active, is how that's normally set up. Here's an example showing multiple devices. So here we have 3, maybe an SD card, thermistor, and accelerometer. And so they all share the clock. So they're all on the synchronized to the same clock. And they all share the 2 output and input lines, and then they each get their own select line. So only one of these should be low at the same time. They should all be high, basically off on the SS1, 2, and 3. Those are the select lines. So only one should be low at a time, and that's the active sensor, and it can, the Arduino in our case, can talk to that sensor and listen to it. That's whichever you need to do. And then it says found here is not a link active on this document, but that's the link I put down at the bottom down here, SparkFun information on SPI. It basically says the same stuff I just told you, but you can read it that way instead of, some people like to read stuff instead of hear stuff. So you don't have to know a whole lot about that, other than it's a little bit different than connecting sensors that you may have connected before. I actually think the thermistor that we're going to use, we're just going to connect it the way you probably connected it in 121. Let's see, what do we want to do now? Not these examples yet. Let's look at this measurement terminology. Let's see what's in there. The PowerPoint. I don't know what it is. It's a surprise. Actually, I think it's about error. So, wow, but it's really formatted weirdly. All right. So these are some terms. Some of them you know, and some of them I've asked some of our attendance quizzes about some of these things. And so this is just things so that we're all talking the same language here on some of these terms. So measurand. This is the thing that you are measuring. So maybe you didn't know that word, but it's not super complicated to figure out what it is. In this box here for generalized measurement system, this is basically 3 parts to any system that we're going to use. One, that there's some way to sense some data. So in this case, you got a thermometer. All of our sensors are going to be digital. So you're going to have, or digital or analog. They're going to be interfacing with our microcontroller. You're not going to read off of a thermometer, for instance. But you have some way to sense some data. Then you have to modify that signal somehow. Maybe you have to amplify it, maybe you have to filter it, maybe you have to amplify and filter it, I don't know, but there's usually something that is done in acquiring the signal. And then you indicate this signal somehow. So in this case, that all kind of happens in the thermometer example here. So we've got the element itself is the well, this probably isn't mercury, but whatever fluid they have in the thermometer. The modification here is that it's going to be forced up this tube as it expands and contracts, and then the indicator is the scale on either side. We can read it directly with our eyes. We will do similar things in the sense that we will have an element, maybe a thermistor. We will have some kind of modification. We're trying to measure temperature with that, but actually a resistance is what's changing, but we can't measure resistance, so we measure a voltage that relates to the resistance, and then we indicate it. Maybe we run it through some sort of code on our Arduino to indicate an actual temperature change. That's just what I just told you already. Let's see. And this is another, maybe not the other, but another important thing is that there's always going to be some deviation between what you actually happens and what your measurement system thinks happens. And then it asks, is this okay? And basically the answer is it has to be okay, because it's always going to happen. You just have to mitigate the differences. So are they things that you can correct? Maybe you can correct it by adjusting your setup. Maybe you can correct it by adding some kind of shielding or insulation, or maybe you can just, some of these sensors you can calibrate. So yes, as long as, and sometimes the deviation is small, so it's not that bad to worry about. Like if you're measuring a length of a football field and you're off by a centimeter, probably okay for most purposes. All right, so error is one of the terms that we need to have a definition for, and basically that's just the difference between what was measured and the actual value of the measurement. So there's a little equation for that. Notice it's an absolute value, so we're not talking about if it's negative or positive error. So here's a little number line basically where there's potential values for the thing being measured. There's the actual value of the thing being measured, and here's what your system told you it was equal to. And so the error is the difference in the two. We're going to, throughout the course, not today, but we're going to work with this error and call it things like uncertainty, uncertainty interval. And so this word uncertainty, I don't know if it means anything yet or not, but what it's going to mean is that we're going to use some statistics to try and quantify this uncertainty. And we can use, remember the tools we use to measure have some kind of uncertainty. So a lot of times you might see a tool, like it's a physical tool, like your calipers, it might have literally written on it plus or minus 0.001. You know, that's some level measure of the uncertainty of this thing. And so if you know some of your tools have a certain amount of uncertainty, you've run a bunch of experiments and you get some randomness in the data, we can combine all those uncertain measurements and the randomness to create some confidence interval, uncertainty interval on, hey, I got this measurement, but I'm not sure it's exact. You know, there's a range of values it could actually represent. So we'll do that later on. So here's kind of the same picture, but now I've taken a bunch of measurements and they don't all land on the same dot, basically. And none of them are on the true value, right? They're all over here shifted over. And so now instead of, previously we called this just error, this distance between true and measured. Once you've taken enough measurements, now and they all are off by some amount. So this black dot here is the average of all of the things you measured. Now I've got some systematic error. So this is actually probably the easiest error to correct for. Basically, you know the true values over here in the red dot. All your measured values are over here at the black dot averaged together. That systematic error you can almost just subtract or add, depending on which way it shifts, from your measurements. And just basically, if I have a value for this systematic error, I can subtract that from every one of these data points, and this average shifts over here. Now I still have scatter. They're not all lined up on top of the red dot, but they're much closer to it. And so systematic error, if you can identify it, is something that you can relatively easily correct for. Maybe you can find what's wrong with your system, like there's something in your measurement system that is consistently throwing your measurements off by whatever this value is. I mean, maybe you can just eliminate it or just subtract it out. there's just an example of it. Random error, so now I've got all these little red X's that don't line up on the average, so there's some randomness. This one's a little bit harder to correct for, but even it can have some minimization. But it might be, particularly since we're going to collect data with the Arduino, and we're going to have wires, and we're going to have analog and digital sensors, then there's going to be room for electrical interference. So electrical noise from a motor, maybe you have a motor or a servo or something, a stepper that is part of your system, and it generates an electrical field when it runs, and that electrical field is picked up by the wires in your system, basically like some kind of back EMF, or maybe just like a radio frequency that's picked up in your wires that are acting like antennas. Then that's going to create random types of error in your system. When I was a student, we had the radio station would interfere with a lot of the measurements that we were trying to make. And I assume it still would, not that it suddenly doesn't, but they did move the tower. It's not in the same spot it used to be. Let's see. So one way to get rid of these is if it's electrical noise from motors or lights, like the lights in here operate at 60 hertz. So our system of power in the United States operates at 60 hertz. And so a lot of your electrical signals, you can see a 60 hertz sine wave riding on top of, or if your signal is a different frequency, then your signal can be riding on top of the 60 hertz. You can start to eliminate that if you know it's there. You can shield against it. That's why your nicer speaker wires are thicker than the cheap stuff. The cheap stuff just has kind of like some rubber and wire inside, and the nicer stuff is thicker coating. There's wire in there, and then there's shielding like around the wire itself, like a little foil around the wire inside the rubber insulator. So you can try to just eliminate listening to the noise. So there's some of that shielding. This is Mylar shielded, and there's a bunch of wires in there. Just the arrangement of the wires themselves. If you have wires, multiple wires that need to go, maybe these SPI, they need 4 wires going to them, the clock and the MOSI, MISO, and the select. So there's 4 wires. If you run them parallel to one another, then they basically create a capacitor, because the definition of a capacitor is 2 conductors separated by a non-conductor, an insulator. And so if you have 2 wires they're conductors, and they're separated by the insulator that, the little rubber coating around them, you've created a capacitor. And so just arranging the wires to where they don't run parallel, maybe they're twisted together. Remember, a lot of times, when you made your thermistor in 121, they told you to twist the leads together, the wires together off of it. Part of that was to make it stiffer and easier to deal with, but part of it's also, now it's called a twisted pair. It's a pair of wires that are twisted together, and that makes it to where it is less likely to act like a capacitor. So there are things you can do to reduce the random error, and there's also mathematical things you can do to at least quantify and use the random error in a meaningful way. That's the definition for random error. So here are back to the systematic error, the one that just shifts everything over. So a calibration error might do that. These sensors, with a thermistor, you've actually already done that calibration where you take a hot and a cold and a medium temperature water and measure them with a known device, maybe a thermometer that's already calibrated. Put your thermistor in those different temperatures and calibrate the thing. Maybe there's an error in that process, and there's a way to eliminate that. And calibration is calibrating your new device, the new thermistor, so that the measurements that come off of it mean something. Because normally these sensors, they don't output the measurement. They output some digital signal that relates to the measurement. So they output a voltage or a current or a whatever, that a voltage usually, that you have to interpret as being proportional somehow to the measurement. So you got to calibrate them. Well, and yeah, there's the inaccuracy of the known values. The example here, the salinity sensor, so the saltwater sensor in 121. You don't have a different way. You just took for granted that you poured this water from this container that said it was 0.01% salt, and you just had to assume that it actually was 0.01% salt or whatever it was. But you didn't actually know that. You just assumed it was. Non-linearity of the output. So you assume that it's nice and linear relationship between whatever your sensor does and the measure end, but that may not be true. It may be a non-linear. So here the little red line is kind of all curved, showing that it's not straight, not linear, where you assumed it was linear. And so you get these data points and you plot a linear line through them. It's going to not overlap that actual line of the thing. So there's this non-linearity that you do have to deal with. Normally how you deal with that is you operate the sensor in some ideal range, and then outside of that range you assume that that data just isn't good. So maybe your thermistor, you just assume it's not going to work very well at 200 degrees Fahrenheit and below 30 degrees Fahrenheit. It's not going to work in those ranges. So you just don't put it in those ranges. Loading error. This is another type of systematic error. So this is where you've got, let's see, there's a picture. You've got some hot water, cold thermometer. You put the cold thermometer in the hot water. It takes a certain amount of time before they're equal. So anytime you have a loaded system, temperature is a good example of this, but even the salinity, anytime there's this discrepancy between the two things that changes over time, so they come to equilibrium over time, then there's a loading error potential. And so a way to deal with that is just don't read anything in that first until you're sure that you've actually reached some equilibrium point. So like load cells, they measure force, and they might have some kind of amount of time it takes before the measurement is actually valid. Easy example is the water, because it's pretty obvious that if this water is hot and the thermometer comes in cold, then it takes a while for them to equal the same temperature. Spatial error. We're going to use another water one, but not every error is associated with water, but a lot of ours apparently are. Those are the things that you've seen in the freshman series. So here's a picture. So I've got a little resistor down here for a heating element. So remember, you had to heat up the water in your fish tank. So this is the thing that's heating, and I've got two different points I'm measuring temperature. T1 is going to appear hotter than T2, yet they're in the same water, because it's just closer to the source of heat. T1 is. So ways you might reduce this are, you just make sure it's well mixed so that the water moves around constantly, and there's not a little bit of volume of water that just basically sits around the resistor, and other water takes a while to heat up. So if you mix and stir the whatever it is you're measuring, if that's possible, then you'll reduce some of this spatial error. So these are all things that are relatively easy to correct, and they will reduce that systematic error, that shift in your data. Here's an example, and we'll code it in Python just so that we can code some Python. So I got a multimeter, and we're calibrating something. I don't know what it doesn't even say what we're calibrating, but we've got 9 measurements using the multimeter. We're measuring the battery, so I don't know I guess we're calibrating the multimeter against the battery. I don't know. But somehow we know that this source, maybe it's not a battery, maybe it's a power supply. So we're more sure that it outputs the same thing every time. So I would actually call that a power supply, because even a battery over time would lose the voltage it's putting out. So we have set this thing that it's going to output 6.11 volts. But our multimeter reads these different things 9 different times. And it doesn't say how often we took these measurements. So, you know, we don't have a whole bunch of details on the design of this experiment, but those would be important. If I took these measurements every day or every 5 seconds, you know, that makes a little difference. So it doesn't, this is just an example. So let's write Python. Now, obviously, you can get your calculator out and do this in 10 seconds. And this would be a reasonable sample of a test problem for test 1. And remember, they're all multiple choice. So this is probably something almost exactly like this is one of those multiple choice questions. So we're going to look at systematic error, and we're going to look at this thing. We didn't actually talk about this, but maximum random error. All right, let's go over to, wow, I've got a bunch of stuff open. Let's close some of these things. I don't think we need that anymore. All right, let's get our, let's do this in Python. I guess we could have wrote it in Arduino Sketch also, but we're going to use Thani and Python because that's what I have it written in. All right, actually, well, let's do a new one. All right, so what we're doing is this. We've got 9 measurements, 5.98 through 6.11. We have a known value, 6.11. We want to write a little bit of code that is going to estimate the systematic error. So what's the difference in the average value of my readings and the known value? And then we're going to estimate the maximum random error. All right, so I don't actually need any particular libraries to do this. It's all just basic math. So, oh, actually I do, because I could do this hard code in the math, but NumPy library does have things like MEEN already built into it. So we'll use NumPy. So we will import that NumPy so I can do some slightly more advanced math than hard coding in the addition and the division for average. We're going to set up our true value of 6.11. We can't do units. It's not MathCAD, so I'm putting the units in as a comment. That reminds me, unless a homework assignment specifically says to use Arduino or Python or write code or whatever, it's okay to solve these things in MathCAD, because MathCAD is nice and does use units, and you do have it, so that's okay. It's only when it specifically says to write code, that means go to Python or the Arduino. We have our data reading, so I call it data, but it could be whatever. These are the measurements that we actually took from our multimeter. So I'm just typing them in. Now, this could be gathered from the actual sensor, you know, if you were recording data from your Arduino. All right, did I get all 9? 1, 2, 3, 4, 5, 6, 7, 8. No, I didn't. I missed something. All right, so 6. Oh, I missed a 6.08. Nope, 08. All right. So there's our data that we actually read in. And then, so the systematic error is the average of my collected data subtracted from, or, you know, it's the difference in this collected data and the VT, the true reading. So we need to know the average of our data. So V average is, in NumPy, lets us do mean. So we don't have, dot mean. It lets us have a function to just take a list and calculate the mean of it. And we could print out, it's always a good idea to print these values out, intermediate values. You can comment them out later, but you want to make sure that all along the way, you're not getting some really weird data point, because it's possible that you make multiple errors. The final answer looks reasonable, but the intermediate stuff is wrong, but you made 2 different errors that kind of canceled each other out. So it's good to print out at least temporarily, all of the intermediate values. All right. So our systematic error, now remember it was the absolute value, so in Python that's ABS, and then the true value minus the average value, oops, ABG, oh I got caps lock on, all right, minus that. And then we need some kind of print command to print this thing out. Let's see, let's just print systematic error, that, and then we'll do plus. We're going to print it as a string, and we're going to round off, so because it's going to have, I don't know how many decimal places it'll have in it by default, but we're going to print out S rounded off to 2 decimal places. And then we'll add in that it is in volts. And we're going to close the parentheses. All right. Now would be a good time to test run this thing and see if we have errors. We have to save it. This will be error example 1. All right. Now let's run it. Oh, my shell is way down here at the bottom. You can't see anything. All right, so we get, so you look at all the decimals. When you don't round, you get all this kind of stuff. All right, so I got it calculating a systematic error of 0.06 volts. That seems reasonable to me. You know, these numbers are all relatively close to 6.11, so I can believe that. It doesn't look out of scale anyway. All right, and the other thing it wanted was the maximum random error of the voltmeter. So what we want to do here is basically find the difference between the average, so the 6.05 with all of the decimals and a 1, and the minimum reading and the maximum reading. So we already have the average. That was, we called it V average. And there's a easy enough way to get the minimum maximum. So we'll call this E for error, equals, not plus. And we're going to equal, and we don't know if these are shifted on the negative side or the positive side, so we're going to use absolute value. Here's how we're going to get the minimum reading, so the minimum of the data list, which is 5.98 apparently. So that one minus the average value, so the 6.05. That, let's see, and then we need to do an absolute value. Oops, ABS. Same thing, but we want the maximum value in data, the 6.11, I guess is the largest one. No, 6.15 is the largest one. Again, minus the average. So now I've got the two extremes, the farthest away from the average on both ends. And I put them into E, so we can print E. Wow, what are you doing? Did I leave off a parentheses? Yeah. There we go. Print E. So we can run this guy. All right, so there's the two extremes down there. They're in a list of just 2 values. And then the maximum of those 2 is the maximum random error. So whichever, it would be the 0.099 should be the maximum random error. So R, whatever you want to call these things, equals the maximum value in list E. So the 09991. And then we'll print that. Print, and we'll set up some kind of maximum random error equal, or well, colon. We're going to print it as a string, and we're going to round it off to 2 decimal places. We're going to round R off to 2 decimal places, and then it is in volts, so we'll add volts on it. All right. Now if we run that, there we go, the maximum, and it did round this number 0.99 whatever off to 0.1 volts. So again, now the maximum random error is not always, I mean, it's nice to know, but notice the way it calculates it, it just takes the extreme data points. So you could have one outlier and it would really affect this maximum random error number. So you could have, if we thought about the picture, well, we don't have a picture here. Let's see, where's the last picture we had? Yeah, it's right there. So I could have one of these readings that's way over here somewhere, and the average wouldn't change that much, especially if I took 40 readings and they were all 39 of them near the black dot, and then one's way over somewhere else. So the maximum random error is not always that useful, but it does tell you something about your experimental setup. It might tell you that you need to change something in your experimental setup, you know, because you've got this one value that's way out of scale with everything else. And why is that? You know, is there something in your procedure that every now and then is not the same as the other times, or why is this something that far off? So maximum random error is not normally something you use, but it can be a troubleshooting type thing if it's a really large number and all your other things are kind of, your systematic error is actually really small. So those two together can look weird, or they can tell you stuff about the validity of your process. All right, back to this. We were down here. The range, I think you know what that is. So here's some kind of hertz meter. I don't know exactly, or maybe this is, I don't know. It's measured in cycles, so it's some kind of frequency of something. And you can see that it ranges from 40 cycles to 60 cycles. I don't know if those are cycles per second, so I don't know if they're hertz, or I assume that's what it is, but I don't know. So 40 to 60, the range is 20, and from 40 to 60 cycles. Accuracy, so how close to the actual true value are your measurements. This, I think, was one of the attendance quizzes, something about full scale. So accuracy is a lot of times specified as a percentage of full scale. So what's the maximum thing that can be read, the full scale of your measuring device. So here's something. It can read in up from -20 to +20. So the maximum thing you can put into this multimeter or whatever it is 20 volts. And then it has an error or accuracy of ±5% of full scale. So your full scale is 20 volts, and it has an accuracy of ±5% of that. So full scale is 20 volts. That's the maximum you can put into the thing. 5% of 20 is 1 volt. So ±1 volt for the full scale 5% error. This is just a statement that it's this accuracy is usually a combination of things. Here, it's kind of small. Can we zoom in? Sort of. That's as much as I can zoom in. So here's kind of a representation of that ±5%. So the red line being the ideal response, it always responds exactly right. But then there is this ±5% full scale. And then this part is circled in here, and it says accuracy may not be acceptable here, because if you look at this, and I can't zoom in any closer, but if you look here, I'm reading numbers that are essentially 0. You know, it doesn't actually go through 0, but they're really tiny. But my ±5% full scale measurements, they don't change here. They're still just as large. So my error is bigger than the thing I'm trying to measure. So this is another example of there are some limits and some points on the range of the numbers you might want to measure that just aren't good. So like on your multimeter, if you have the ones with the dial that has 20 volts and 1 volt and 10, you know, all these different ranges, that's to take into account this kind of stuff. Sure, you can put it on 20 volts and measure 0.2 volts, but at 20 volts, your full scale is 20 volts now, and it might have this 5% error. But if you switch it down to 2 volts, now your full scale is 2 volts, and your 5% of 2 volts is smaller than 5% of 20 volts. So some of you have multimeters that do that automatically. They auto range, but I know some of you probably have the ones where you have to select the right range, and that's why, because if you have a potential error of 1 volt plus or minus, but you're trying to read 0.2 volts, then that doesn't make a lot of sense. Let's see what else we got here. This is just talking about accuracy. You want to measure a temperature that's about 80 degrees Fahrenheit. You've got these available thermometers from McMaster-Carr, and you want to pick one of them. We assume they're all the same price. I don't see any prices on this. They're all on the same list. We'll assume they're all the same price. So there's not a price issue that you're trying to minimize. But some of these, they go from -40 to 160. Here's some 50 to 500. They're all different ranges. They all have plus or minus 1% accuracy, and you have to assume that's a full scale. It doesn't actually say on this sheet anywhere that this accuracy is plus or minus 1% of the reading or plus or minus 1% of full scale. If it doesn't say, probably means full scale. And then this little column is just telling you how often the marks are on the dial. And so we want to measure 80 degrees. So basically what you want to do is you want to find one that, assuming price is not one of the factors, then you want to assume that this 80 is somewhere in the middle of the range. So this one right here that goes from -20 to 120 puts 80 pretty much right in the middle of that, and it has 1 degree marks on the dial. So it's got a little, if it's a visual, these are analog, so you have to read them yourself. So it has a little bit more resolution on that, at least on the marks that are given. And it still has the plus 1% full scale accuracy. All right. And that's just what it said. Then we've got this idea of precision. So we just talked about accuracy being close to the actual thing measured. Precision is the ability to repeat your measurements. So you get the same thing over and over and over again, but it may not be accurate. So you can be precise and not accurate. This would be kind of precise. All the X's are kind of close together, but they're not landing on the true value. Here you've got, they're closer, but you've got some that are way over here. So this is not very precise. You've got a lot of precision error here. Here, you're very precise. They're even tighter together, but they're not accurate. Here, this is kind of what you would rather have. They're close to the true value. There's some error, but they're not scattered everywhere. So imprecise and inaccurate. Got a little bit. I said that this was kind of close together, but it's not as close as this one. This one is accurate, sort of. I mean, you've got some that aren't, but you've got most of them. The average of them is relatively close to the true value, but they're not precise. They're scattered pretty far. Here is precise but not accurate, and here's what you want. You want all your data to show up more or less in the one spot, near the true value. Resolution talks about the smallest thing you can measure. So on a multimeter, it's the last decimal place. On a ruler, it's the little marks that you have. You have to be careful with these. Just because you have this decimal place doesn't mean you actually get that resolution. Sometimes it counts in multiples that aren't 1 unit. Sometimes these okay. Like I'm actually curious. I think actually these multimeters do 4.94, 4.96, 4.98. I don't remember. But you have to, you can be tricked a slightly, a tiny bit with that. Yeah. There's another, a zoomed in wooden ruler. Not very, I mean, not your ideal thing, but you could go in and try to, divide this thing into a bunch of little estimates. It's usually best to just go in and pick one of the actual marks on the ruler. sometimes you're told to estimate a half or not. You'll get more consistent readings if you always measure to one of the actual values versus estimating. But kind of depends on what you're trying to do. Well, that's what I just said. It's usually best to go to the markings, not try to guess. And then repeatability is you get the same thing over and over. All right. We talked about linearity already, where there's could be some nonlinear response from your devices, particularly when you're dealing with these devices that are going to be converted to digital. There are reasons, and we'll get into analog to digital conversion later, not today, but there's reasons why it might not follow the way you expect. Let's see. Those are just, you can look at that. Here's a nonlinear. The scale is not equally divided, so in the middle it's kind of spread out, and the ends it's kind of not spread out. So they're accounting for some nonlinearity in their response. There's probably a little spring or something in here, and they're basically just marking the readings in a nonlinear way so that it can be read. So it's the actual thing is nonlinear though. Sensitivity is the change in your measured value compared to the change in the thing you're actually measuring. So how sensitive is it? Here's an analog device, the thermometer, and a digital device, the accelerometer, that kind of demonstrate that. Drift, this one, so your measurements over time, particularly when you're using, well, not exclusively when you're using electronics to measure things, but electronics do have this problem, is that you can measure like a load, a static load on a load cell, and it will measure different amounts over time, and it's not because the weight is changing or anything, it's just because the mechanism being used to measure force is dependent on strain in a piece of metal of some kind. Normally is how that happens. Could be a spring, but a lot of times it's a strain. And the metal itself will creep over time. So it will actually deform just under the load, and it'll look like the weight is changing, but it's actually not. And so this will show up as drift in your data. Other things can cause drift too, but this is a thing that you may encounter, because we're going to, at the end of the quarter, near the end of the quarter, you're going to do some 24-hour measurements that might drift over time. So you might have to account for that. Things change with temperature changes, that maybe that's not what you're actually trying to measure, but a lot of these sensors have temperature correction factors associated with them. So as they get hot, they measure different things. Maybe they even self-heat. The thermistor, you have to run power through the thing for it to work, and so it might heat its own self up and measure a change in temperature. So there are temperature changes that you have to take into account. And here's our last little deal. This is just an example. So we've got, and we'll code this one in Python too. We've got an angular velocity measuring device. So this is a tack. So something that measures how fast a shaft is spinning. Or sorry, it doesn't have to be a shaft. How fast something is spinning. And it can measure from 0 to 5,000 RPMs. That's its range. It has an accuracy of plus or minus 5% full scale. So the maximum thing it can measure is 5,000 RPMs. So we have a plus or minus 5% of 5,000 as our maximum error there. You notice that when the shaft speed is 0, so the shaft is sitting still, but your tack says it's moving 200 RPM. So it's spinning at 200 revolutions per minute. So there's some offset error here because it's not moving at all, yet your device tells you it is. So what we want to know is what's the maximum error that we can estimate if the shaft is going 3,500 RPM. So let's go over here, write us a new little bit of code. New code. Let's see. We don't need NumPy for this one because we're just going to code in the math basically. So the range for this thing, for our measuring device, was 0. It could measure from 0 to 5,000. Oops, that. And that's in RPM. So the accuracy, so the resolution, equals, so I'm going to put 5 in here and then just put that is in percent. And then we had what I called a Z, or well, I didn't call it a Z offset, but it is an offset. So remember when the shaft wasn't spinning at all, our device, our tachometer said it was going 200 RPM. So it is off by 200 RPMs. This would be a systematic error. So I'm just going to code that that's 200, and I'll then put that that's in RPM. And so both of these things combined together will give us a way to calculate the potential error. So our speed that we actually think the shaft is going is 3,500. My cursor go. And that's RPM. And then our error, well, this is the error based on the resolution, so the 5% off. So resolution, whoops, I capitalized it before. Resolution divided by 100, so I'm turning it into a percent. Since I wrote 5 in the definition of the thing, I'm going to turn it into a percent this way. Times the range. And I could do max range, or I could do that. I'm just going to do range element 1. So remember, range element 0 is the first thing, which is a 0. Element 1 is the next thing, which is 5,000. So I'm accessing it that way. I could do max, though, to get that also. We could print that out if we wanted to. That's just the error from the 5% of the scale itself. And then we have the offset error. So it is already coded in at 200. So the max error is these things added together. Resolution error plus what I called Z offset, but you might want to call it something else. And then you can print the maximum expected error is, and then you can add in, we can make it an integer, max error. Close those parentheses, and then we can tack on that it's RPM. And notice the 3,500 doesn't actually go into this at all. So it doesn't matter. Neither of these errors change whether I'm reading 0 RPM or 100 RPMs, 5,000 RPMs, 3,500 RPMs. These are built into the system because I assume, I have minimal data here. You probably should take multiple readings to see if it's linear. We don't have any information that our response is linear. We assume it is. But this offset is going to be present in any error. And then our plus or minus 5% is always going to be true also. So let's run. I'll have to save it. I haven't done that yet. So what did I save the other one as? I don't know. It doesn't matter. This will be some kind of. Oh, there it is. All right. So we'll just put this is number 2. All right. So let's see if we get. So 250 was our resolution error. We printed that out. Got extra space in there. I don't like that. So our maximum expected error is 450 RPM. A little space after that. There we go. Maybe a period too. So if we wrote a sentence. All right. Now we could have a little addition to this. Could be like, all right, if I am measuring 350 RPMs, then what's the range of values I could get? Because I've got this 450 RPM potential error here. You're not guaranteed on this resolution area, you're not guaranteed that you will get 5% off. You're just up to plus or minus 5%. So you may get exactly 3,500, but you might get, 30, what was the, 3,700, and you might get 3,600. You might get all these numbers in between there. And that's where the probability stuff later on, not today, will come in, is figuring out how uncertain are you about these measurements. So you've got homework 2 that has you do some sample problems like that. Most of them you can do by hand, MathCAD or whatever. There is the one that you do have to write a Python code because it's going to ask you to plot something. But most of them can be done in however format you want. Make sure your SD card, I guess I closed mine down. Yeah, I think I did. Make sure your SD card works and run it through the SD write all the way through that to make sure it basically says that it can write to the SD card. If you're good on that, then that should be fine. And then you've got one thing on, I put it thermistor data collection. Part of this PowerPoint walks you through, I know you had to do it because you've already done it, but it walks you through setting up your thermistor to take measurements. So basically you have to solder on some leads to your thermistor, and I'm not going to walk through this, but I'll show you right somewhere. Here it is. You got to make one of these things, and I think you have some heat shrink also. I don't know if we have the liquid electrical tape. Did we give you heat shrink in the? Okay, so you could either put the heat shrink on it, and remember you can clamp that end. Don't crush the little bulb on here, but you can extend the heat shrink out past it and basically clamp it with some pliers, heat it up and clamp it, and that'll seal it up. You just don't want this to be exposed to water because you'll get bad readings. And also make sure these don't touch each other. So make sure you run heat shrink all the way up to the end. Then there's the twisted pair of the leads, and you need one of those so that you can do some data collection with thermistors. And then if you want to test it out, there's a little piece of wiring right there, shows you how to connect it. All right, Thursday we're not meeting here. You can go to career fair, get ready for that. And the lab now has 5 setups in there that you can solder with if you need to go do some soldering.